Just for your information, you know this firmware day3, right? It is a firmware written by open source groups that can be installed to various devices. And it gives you great flexibility that the stock firmware doesn't give you. So you can change a lot of things, apply extra security measures, do tunneling VPN tunnels to home from the world. So one good communications engineer should be able to do such things. There are two types of firmware, DD-WRT and OpenWRT. They don't support all the routers. Your first thing to do is to check if the router supports one of these two firmwares. And if support, go purchase it and you can do great things. Personally, I love Asus Merlin, which is intended for Asus routers like this one. And some of the models are extremely powerful. Actually, they are equivalent of commercial grade communication device. And you can do a lot of network. The main thing is you set the router to some of the providers of how do you call it?
ISPs?
VPN services, like NordVPN or Surfshark, yes. And all your router directs your traffic encrypted in an encrypted manner to the VPN provider, and then you go to the world. So there is no way that your internet provider can sniff your traffic or anyone else in between. And the first benefit of this, you have great privacy over your stuff. Second, you can set your provider to change the IP address every time. So trackers, machines that build your digital twin are not able to track you so very successfully. So you can kind of counteract to the Big Brother, which is very popular nowadays. You can do torrenting, whatever you want, without being constantly monitored. That is the purpose of this. Okay. The main rule of thumb is get the router with embedded coprocessor that helps the encryption. So during the encryption process, you won't see a decrease of the service speed. Some of routers, they have dedicated processor that helps the encryption. And the best protocol so far is OpenVPN. This is the top-notch security. You basically doesn't need to know anything else. And the second one emerging is WireGuard. WireGuard requires much less processing power, so you can install it on your cell phone. And your cell phone service provider is out of the equation. This is few hints about surfing safely the internet. And now, a few words about arrays. What is antenna array? Array in English means a battle order, battle row, or set of something. In computer science, it became very popular, a set of numbers with columns and rows. We call this array, and then we can address each cell of this array, and we claim IT professional. I know arrays, and I know variables. I know how to make a loop, and I need big money because I'm a programmer. A lot of people imagine this thing this way nowadays. Unfortunately, this is not programming, and basically nothing. But today we live in such times. And what is array in antennas? Let's get the first example. We have a dipole located here, and identical dipole located here, which are pointed from us toward the screen. The distance between them is d over 2. This is the central line. We give them same power and same phase. It's easy to provide. We get a cable. We put a cable and then split it by 2, and with equal lengths of this cable, we feed these two dipoles with the same power and same phase of the signal. And we would like to estimate the field strength in point P. And how to do that? Easy. We write the equation for the field strength for the first dipole, like we learned that yesterday, and it will be a constant times the pattern times the phase component. This E minus jk r beta over 2 gives us the phase of the A vector over the distance times something that is responsible for the current in the dipole 1. And we can write almost the same thing for the second one, second dipole. So, constant, pattern with the angles of direction, the phase of the field over the distance to the point times the excitation coefficient. And if we get the point P far enough, very, very far enough, we get to that. That's it. So the three vectors R1, R, and R2 are parallel. So the angles theta 1, theta 2, theta 3 are identical. And we can assume the excitation coefficients P1 and P2 are equal because that's by default. We fit to same currents. And the total field in this distant point P will be sum, vector sum, of the field from the dipole 1 and the field of dipole 2. And we get the pattern and the coefficient out of the brackets. Distance is also out of the bracket. And we got this expression inside the bracket. And having this expression, sum of exponents inside the bracket, we can apply the Euler formula, and we get to that equation. Amplitude component, pattern of a single dipole, vector phase component of the field over distance times 2 cosine this expression and this expression on the back. And if we carefully take a look on that in a blue rectangle, what we can conclude, what this is similar to, do you see some similarity with things before that? It looks like formula for antenna pattern. Is it?
But it's the sum of two antennas.
Yes. It looks like formula for antenna pattern. It depends only on theta, nothing else. Beta is 2 pi over 100, so it's constant. This is constant. So we have cosine of some angle of arrival, or direction of transmission. So if we have a set of 2 dipoles, the sum overall pattern in general of this set is multiplication of the pattern of the dipole itself and the sum product of these 2 dipoles. That depends on the distance between them and the wavelength and the angle. And this second component, second antenna pattern, is called array factor. In Bulgarian, множителна решетка. In English, array factor. And this array factor gives us the idea how the array will perform depending on the position of the elements of this array and the wavelength. So what is an antenna array after all?
A pattern of multiple antennas.
Set of multiple antennas that has common feed and common phase or phase distribution. It may not be equal, it may be linear shift to somewhere, linear increase, linear decrease, or something else. And this set of identical antennas gives us an array pattern, which we multiply to the pattern of the single element, because single element may not be only a dipole, it can be a horn antenna, like in case of, if you remember the wall with many horns that was meant to detect ballistic missiles. They have highly directed pattern. So this can vary depending on the construction of our array, and this depends on the position of the single element within the antenna array. Yes?
Could you ask about a couple of parameters that I forgot? For example, what was beta?
Beta is the wave number 2 pi over lambda. Beta, yes.
And then also that distance d is probably.
Oh, I'm sorry. Beta is the here is the phase shift between dipoles. So if we introduce phase shift, it will change the direction, as you will see. K is 2 pi over lambda. I'm sorry.
Yeah, that's the wave. But what about d? It's probably.
D is the distance between the dipoles.
Yeah. And just one last question. When we wrote the power or the field emitted from each of the antennas separately, there still was this vector rho at the end. But now, like, I wonder how we get the value of
That's what?
of the vector in the last expression.
This one?
Yes, of the last.
This one?
Exactly.
This is the number related to the magnitude of the current that excites the field. Like 1 amp on each dipole, 1 amp.
Isn't it a different number when we look at the antennas separately though? For example, in the previous slide, I think the one before that, maybe. Yeah, we had.
P1 and P2, but we assume we excite them with the same current.
Okay.
Identical current. And that's what array factor is. The pattern of the array is a multiplication of the pattern of a single element times array factor of the given set in the space. So this is easily calculatable with a simulator, like for NEC2 that we will going to learn, or at least get a grasp on. And this can be mathematically derived. And why we use mathematically derived array factor? Because to simulate a large array, we don't have enough computer power to simulate it explicitly. And so far, all engineers work this way. They model or create a single element, working long hours, and delivers the pattern. And then in MATLAB, they calculate the array factor for specific array distribution. You will see in the next lecture, which David from Astron will give it to you, how they came with the distribution of the antenna elements. And their distribution is pseudo-random. It's not an ordinary array. And they use MATLAB and simple simulators, not as simple as for NEC2, but a little bit more complex. But not that complex that we use here, actually, like ANSYS, which is heavy artillery. For NEC2, it's like a slingshot. You can kill a bird, but you cannot win a war with it. And they use something more complicated, like a bow or crossbow. but not the machine. So we model this in Fornecto and get the pattern and play with MATLAB to deliver the array factor, and then multiply these two again in MATLAB and deliver the pattern of the whole antenna array. And that's how all arrays are built, from very simple to very complex. And now, in the recent months, can I show you the paper that I recently wrote? I'm not so sure if I have it here. Yes, maybe over here. Yes. This is how the single element of the low-far array looks like.
Would you duplicate the screen?
This here is how one of the elements of this array here looks like. And I've made the real model, including the grid and the soil underneath and everything else. So this is the radiation of the actual antenna, accounting for the finite conductivity of the soil, conductors, and everything else. And here you can see the difference between real life model and what Fornecto or something similar that makes approximations. So it takes the ground for perfect, it doesn't account for the grid, etc., etc. So you see a huge difference between these two. And then recently, technique called component element is introduced. So you make component of an array and simulate just the component. Then you simulate just the empty space. And then software fuses the fields from one component to another, and you don't have to calculate the whole array in the same time. You just calculate the fields within the components and apply mathematical summation.
Like
Not
superposition.
Yes, superposition. Not simulation of the whole array, which is impossible. Undoable with desktop computer. You need supercomputer, but we don't have supercomputer. So this is, but until recently, until last year, this wasn't available. So we have to resort to the classics that I just mentioned to you. Calculate the compute or simulate the pattern of a single element, and then multiply it to the array factor, which is good but approximate. And you go for fabrication, you go to real life tests and see, oh, something doesn't work as expected. I have to go back and rework something or make deep conclusions, which are often wrong, etc. But that's how engineers work from Michael Faraday until last year. And now let's see an example of an infinite small dipole. Lambda over 4 apart. So here is one of the dipole, here is the second dipole. This with green are the patterns of a dipole, quarter wavelength apart. Between 0, it means dipoles or radiators are one over the other, until lambda over 2, they produce a nice uniform pattern. If the distance between elements exceed that length, lambda over 2, patterns start to deteriorate. It simply breaks, forms two small patterns, something that we don't want to have. So we have to keep an eye on this dipole distance, element distance. And here we have the pattern of a single dipole here. Dipole is here. And this is the pattern of the array factor. And when we multiply this to this, we get this result. We see a little bit of a gain in some direction. Good. Here is the condition. Number of elements 2, no phase, and distance lambda over 4. So the summary pattern is over here. And what will happen if we introduce a phase shift, 90 degrees phase shift between dipoles? The pattern of a single element will remain the same, but the pattern of the array will look like that, and when we multiply these two patterns, the resulting pattern will be this guy. It means the array will start to shoot the energy in one direction. And what will happen if we just do nothing else but switch the phase to minus 90 degrees?
We will rotate the pattern.
Exactly. It will rotate from this position to 180 degrees in reverse. And you will see that on the next page. Bang! Nothing changes except the phase shift between dipoles. And we get a pattern that radiates in completely opposite direction.
But it is impossible to have just one directed pattern. We will always have side leaves.
Lobes, yes.
Lobes.
Yes, that's how antenna works. If it was possible, there will be less need of antenna engineers, and we have to do something else. It's like pharmaceutical company. If they introduce you a medicine for all disease, they will get out of the business very soon. That's why they sell palliative medicines, not the, in most of the cases actually. And here is how typical array factor of multiple radiators looks like. You know, with blue is, let's say, 5, with green, red is 10, and green 15. The more elements, the narrower the pattern. And that's how the large array of LOFAR works. It has multiple elements, and that's why it has very narrow pencil beam, main beam. And you can watch part of the sun. Oh, I see here black spot, let's look inside. Oh, I see here something else, let's look inside. This is how it is made. So this is the whole science of many textbooks, thousands of pages to learn, compressed in 20 minutes, actually. But I hope this was kind of just enough to pick up the idea. Yes.
I have a question about the main idea actually. You said that the LOFAR array works with many elements so that this pattern gets so that it gets more clear in one direction.
Narrow. It's like a
Narrower, yes.
small hole that you watch through, and you can, if you move it, you can.
Yeah, as if adding more and more dipoles.
Yes.
Yeah.
And now I want you to grab the Fornac 2 and build your first dipole.
Is it true that if we have 3 dipoles, we can move the beam in 3 directions, like in the 3D space?
Yes. That's how you have to put them in a plane, and you can make a two-dimensional, three-dimensional scanning of the beam.
That's how the American big
Really works.
yes.
So we go to Fornac 2 and download. Oh, we have already preset an example here. Very simple. And if we open the editor,
Oh, you can't see the screen.
Yeah, we can see the screen.
you see the dipole, very simple. Easy. And you go here, settings, and select Make Editor New. And when you click to edit, this edits the geometry. And we expand the geometry file. So there are several types. The geometry file is the file that describes the geometry of the dipole, of the antenna. In symbols, we can introduce variables, descriptions, something like that. Here, in geometry, we have first description of the conductor. It's a wire, but here, but it could be a load, it could be something else. Tag number is simply like a label of the line. Number of segments, this is the number of pieces that simulator will divide the wire to smaller elements with constant current. So over the dipole, current is not constant, but for simulator to simulate them, it divides the wires to small segments with a constant current to each segment, calculates the field radiated from each segment, and tunes it in the far field. And that's how this is called method of moments. And that's how this simulator works.
Is this because when we actually make an antenna, it is divided by segments of constant current, or is it just for the sake of the simulator?
First, for the sake of the simulator, and second, we have to divide it. Otherwise, it cannot.
It's an integral, and
yes.
we basically define the steps.
Exactly like that.
Which is
And then next 6 numbers are the x, y, z of the beginning of the dipole and x, y, z of the end point of the dipole. That's how geometry is defined in space. The last number is the radius of the dipole, and the last line, the last cell is the command, which it doesn't take into account. The next step is the source. So the simulator, we tell simulator put a voltage source on segment 5. So if we have a dipole of 9 segments, segment 5 will be the middle. With 1 volt excitation, 0 imaginary part. So you can define the voltage as a real and imaginary number, or magnitude and phase. And this is how, if you make a set of several dipoles, you can introduce what? Array with a phase difference between elements. Frequency is defined 300 megahertz, no ground. It means dipole radiates in a free space. From here you can select a ground. Eventually you can play at home with that to see how the ground impacts the radiation from an antenna. And then some other things that we don't care very much about. We click save, and then we go to the calculator. Use original file and calculate for us the far field pattern. When you click generate, lighting fast, the simulator calculates the pattern of this antenna, lighting fast.
So on the calculator, how did we get these values? Or you had them pre-populated
Which values?
on the calculator?
Here, you click here and it asks you what to calculate. Far field pattern, and then you click generate and it simulates the dipole and spew out the result. And tell me please, in which plane we have cut the pattern? if you look at the dipole, which is the plane?
XY.
X, Y?
What do you mean cut the pattern? Oh, like the cross section.
Yes.
On
On engineering slang, this is cut. But it is
It should be in Z, right?
Z, O, X.
Oh, in
Yeah.
ZX. Yeah, through the middle of
Yes.
the dipole.
Exactly. And if you want to see the pattern in another plane, other cut, you simply this should not be like that. This is the dipole in 3D, and this should be able to show the pattern in 3D viewer, but for some reason you see the other thing is the simulator can show you the current distribution over the dipole. So if you click here, current magnitude, it will draw you the current distribution. But what I'm interested is to see how the 3D pattern was meant to be displayed. And there was additional over here. So we have to install an extra software called GNU Plot Freeware. Yes. Then no.
Should we download GNU plot as well?
Yes. If you want to see the 3D pattern, yes. But I'm more concerned about why it doesn't show the pattern in the other plane, which is kind of a secret for me. So in this plane looks good, but it should be also in the other plane, which is kind of a figure of 8. And that's the 3D pattern is of great help because sometimes you don't make assumption. This is, guys. This guys is the problem with the freeware. Sometimes it works very well, sometimes not so well. Here, from the, maybe it's better to download the version from the Forlac main site, because the others, the original seems to make problems with.
Well, was there an executable? On the one you downloaded? Or is it just an extract?
It was just an extract, I don't see execute.
Did you change her title? How to change the example? How do we edit the charge? I found it like this. I can edit the out file. Yes. Data segmentation. It's pages now. So, yeah, because you see something is like from here, you can say which ones. You can edit it.
Finally, we got it. On a plot 3D viewer, here you go to a multicolor pattern and you can see how your antenna radiates. This is.
Why is it different though? And I got the first picture you got with the 4 maxima.
Apparently with blue plots on a plane and here plots in 3D. So the gain is good for a dipole, 2.1 dBi. As you see, engineers put dBi as antenna gain. And your antenna is inside. This is our antenna. With the dipole is this and this. And with this pink dot inside is the source. Here we inject the voltage signal. And what I want you to do is to put an extra dipole like that, half meter away from this.
Can you show us again how did you change the view plot?
From here, you go here, pattern, and it plots. 2D slice to the multicolor pattern.
Okay.
And the multicolor pattern gives the game. Okay, let's try now to put a dipole. We open the editor and we just have to copy this line and paste. And
Change the coordinates.
yes, just add an extra value for
X.
x coordinate, let's say 0.25. Let's not be a 0.5 half meter, 25 centimeters. So the first point will be x 0.25 and the second point will be 0.25 meters. We save it. And let's plot the geometry. Oh yes, duplicate tag, so this will be tag 2. Save. And then show window geometry. And you can see here in the geometry editor, we have a dipole, the driven element, with the source here, and an extra element which is parasitic element so far. Correct? Correct. So this is a simple yeah. And now we click here validate, run geometry check. Geometry editor tells us you do everything very good. And then we go here and calculate the field, the non-far field pattern. Bam! And what we see that we have built our first directive antenna. Here is how our thing look like in 3D. We have the dipole and we have the director. And now we just have to put the pattern. And what we can see, our parasitic element actually reflects.
Okay, that's fine.
It doesn't direct but reflects the power.
How do we save the changes we've made in the edit file?
We save it with this when you open the editor and you click here on the floppy disk.
Okay.
I know you guys never have seen a floppy disk in your life.
Let's try.
I never imagined that we'll get to this. That's life. And we have a gain of 6 decibels. Ta-da! We are oriented engineers. We can build something.
Yeah, you could also do it this way. I don't know how this comes out. Yeah, can you go here? Can we have a question?
When I try to edit the files in my
Yes, because you work with geometry editor and work directly with text editor is much less. Just open the text editor. You go here, settings, and click here, next editor. And then when you click edit, here, remove it, yes. You can edit the lines. Take it away.
So you cannot copy paste. Yeah, but yours is not the Bible. So maybe we'll go to example one. So control you can use one person or here. What is it? Copy the line. Choose that to the same everything.
Just
Hitting enter like that. Let's go. Like this.
Duplicate text. So
Did you understand? Now go to
Save as the да, и след това какво
now we want to have just same thing, same length, same position, just shifting x. So we just add x value. X1, yes. And for one of the other. Yeah. So let's do product. The x coordinate of one variable and x coordinate of the other. Okay, that's fine. Now click save. And now let's go back to the calculate screen. Here, calculate. Calculator. This one. Here. Yeah. Okay, now let's go to there's so I guess you could also edit with like geometry, like you that's the same thing.
The exercise. Can you help me?
I don't know what the exercise is. Was it this one?
No, this one.
Ah, this one?
Yeah, just
Is there a next one?
No, I don't think so. So I did the data here and I tried to save it, but for some reason I don't. Yeah, on this. Just
This is
not what you guys got though. Did I mess up something? Yeah, okay. Oh, it's like sandbox anyway. Yeah.
Does everybody got this nice Yagianta? And now, guys, I want you to introduce a source here and see how the combined array will work.
A source like another level?
A source like the source here, source of voltage.
Okay. So where do we put that other source? Somewhere on X or Y?
In the middle of this parasitic element.
Okay.
In this manner, you will make it active, and you create a simple array of two elements, and manipulating the face, you can start scanning.
I have a question. Can you look at my data? I'm not sure if I entered everything correctly because I'm not getting the same graph.
So the dipole is good,
Yeah.
and you just have to, it's 5 meters apart, that's
Okay, so yeah,
0.5.
0.5.
And the other point also is
It doesn't in meters. Okay.
So on the source side, I don't see the coordinate where you put it.
You put the source, you go to a top source, I will show you right now.
I copied the other one and I see like a fact, segment, real, imaginary, magnitude, phase, but I don't see like the coordinate.
Let me see. We open the text editor
Yeah.
and we go to source load. And we have only one voltage source. And then we want to put second voltage source. On which tag? Tag 2, segment 5,
Yeah.
real 1, imaginary 0.
Okay.
And save.
So when we say it's tag 2, it's automatically going to put it on the other one?
Yes, as you can see.
So then we calculate again?
Yes.
Natalia, did you say the real part of the curve was
1.
Real 1, imaginary 0.
So it became a array.
Yes, exactly.
Okay. It cancelled out the deformation. Source, did you create another source? So go to this tab. Then put code. Yeah, so I have to create another source. Same on this one. But tab 2. But you changed the existing source, it's just
Okay. For some reason it didn't calculate for me, but I hope you have better luck at home. And guys, I would like to introduce you Mr. David Prinsloo from Astron, Netherlands. And he is the author of the array, so he can...
Unfortunately, I can't take that honor. It was my colleagues that started just before me.
Lucky you, you don't have to work.
Yeah.
Because actually the antennas are not very good, so...
yeah. You know too much already.
At home you will practice this, you already know almost everything. Build some rhombic antenna. Do you need something to connect the
Yeah, just yeah, an HDMI cable.
not so thick? Do you have one?
I did not bring an adapter for this.
Oh.
I think I want.
Само тага на сегмента.
Мога да. Последната за винта.
Това е тага, но това е това практически сорса.
На мейл или на Viber?
Да, ако ти е тага две, да, Excel. Ако ти е нещо друго,
Or if you need to write something, you can pull up the screen and write on the.
As well, yeah,
Whiteboard.
I also, if I can, I'll also cut on the whiteboard.
Yes, so here the pens.
This one should work.
If you need internet, radio 2 is the SSID.
Yeah, I've got it on, I think I used CIW or CIM, but I can add on radio 2 as well. For some reason this one's not detecting the display.
Really? Let me go grab something else.
Oh, something's happening. Yeah, there we go.
Do you guys need a break? Yeah. 5 minutes break. Bravo.
Ще ви дати лаптоп, що? Лаптоп ти ще ми
Не. До края мисля, че не. Утре. Утре с... И колко е?
Кое да остане?
Дали да напомня да влезе малко широко?
няма да е лошо.
Вие се чувствате свободно да правите какво да намерите за добре. Може и да става да се отвори, може и да искате само да не прекалено много на това, кой ще се и така, и отпред.
Аз ще ви го
Да. Там, където е цветето, все пак за нюха може. Това е топло. Ку-ку. С дистанционното вашия лектор може да се гласи презентацията.
Смисъл?
Ами, да не е толкова голям екран. Ако има проблеми,
David, you can switch the screen resolution from here, I guess. With the HDMI. Not this one. Aspect. This auto.
It's widescreen, but if it fits better like that.
I think this should be the position. We just have to bump it
A little
a
bit.
couple of times.
Right, spot right? Yeah.
It's better.
Okay, we'll leave it like that. Perfect. You see.
And maybe the focus a bit of the zoom. Is it focused?
Now a little bit, you got it good, it's going the wrong way. No. There we go. That's good. At the back as well? Yeah. Seems like we have an intense week. If I look at the program, it's quite full.
Yeah. The whole theory.
The whole theory, yeah.
Yeah.
So, well, just like
And we also have practice in the
you have labs as well.
in
or-
the labs. Yeah.
Yeah. What are you doing in the labs?
The first one was when you have an obstacle by terrain and you get obstacle of a Fresnel zone.
Oh yeah, yeah.
Yeah. The second one was to calculate the gain of the antenna.
Okay. Yeah.
And the third one was to calculate the pattern of the parabolic antenna.
Alright, so actually, that's a simulation or are you calculating
No,
the
no,
pattern
you
of the...
You make measurements of
Yeah.
the signal.
Okay, yeah.
You have a test bench.
Of the parabolic antenna.
Yeah, a small parabolic antenna
Yeah.
and the receiver.
Okay.
And you take notes of the measured voltage.
And you did this outside? Or
No, in the lab.
in the lab, yeah?
Yeah, here.
Are we waiting for anyone else? I see one laptop empty. One more person.
Yeah, I guess one more.
So it's everyone. Okay, then I suggest we start. Yeah, as Peter introduced, David Prinsloo from the Netherlands Institute for Radio Astronomy. By, let's say, education, I'm an antenna design engineer. I did that for 5 years at Astron, but now I'm a group lead, so I don't really work with antennas myself anymore. I work with people that work with antennas. So I can give you almost a second-hand experience here, but I do like to follow antenna development as much as possible. I'm also 1 day in a week at university in the Netherlands, Eindhoven University. There I supervise some masters and PhD students as well on antenna designs mostly. If I can define a project, it's typically has to do with antennas. And I noticed that you have had quite a crash course on antennas the last, I can almost say 2 days, because you started with electromagnetics and now we've gone all the way through to, well, even antenna arrays that you just did a demonstration on. But just for myself, to get in a sense of what your backgrounds are, if you can maybe open your cell phones and go to menti.com or on your laptops, I'd just like to see who you are in terms of education. So I've got a few options. If you go to menti.com, there's a code you can enter 7880, that code. And if you can just say which one fits you best. I'm just curious to know your backgrounds a little bit. Seems to be working. Not to put anyone on the spot, but other. Who is the other?
Me.
Yes, and what is other?
Well, I'm not in university yet, I'm a student. but I study physics.
High
You
school.
study physics. Okay,
Yeah.
so not at university level yet.
Yeah, yeah.
Okay, yeah, makes sense. And a large number of bachelor engineering students then. Okay, so this is already your first introduction to antennas, I assume, that you had here now. Or have you had antennas in your coursework before? Okay, and maybe the next one will answer that. I think that most of you, or some people, still need to log in. If I'm not, we are 12, if I'm not mistaken. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah, 12.
12, yeah. So I'm missing 2, I think. Anyone not got on? Okay, well, you've got another chance if you want to try again. Let's move to the right of the screen. There we go. So which antennas have you designed or worked with at least?
Yeah,
Other than today and
Other than
this week.
today. It's fine, you can just say no. No. Okay, so someone has worked with arrays. Who is that? Yeah, what type of array?
Yeah, I work with local data for
Okay,
my thesis.
I work with low for data, yeah. So you're doing physics as your background, I assume.
It is
Okay, yeah. So you work with both the LBA and high and low band antennas?
yes, mostly LBA for the band spectrum and
Yeah.
the imaging.
Okay, yeah. And someone worked with a reflector antenna. Was it, I assume you, if having measured one?
yeah.
Yeah.
With DHL antennas, DTH antennas.
Okay, yeah.
So we deliver them with wall voice box for mobile operators.
Alright, yeah, so you actually install these and deliver them?
Yeah.
Okay. But then I'm glad to see that most of you none. So then, well, that's good because that's exactly why I'm here to introduce you a bit more on the antenna concept. Although looking at the flipboard, I think what I will be doing at the moment is just testing how much attention you've paid, as I am running through a lot of a recap almost of what you've done, especially at the start. But I want to tailor it a lot more to radio astronomy, as that's our background. So just to explain to you why we use the antennas we use in the radio telescopes, like LOFAR. So if that message is clear, then my work here is done for today. I can go to see the next one. Yeah, we'll get to that point. So, getting back to the presentation. Have any of you visited Ostrom before or not?
No.
One person has. Okay, then I feel obliged to just start my presentation by showing you an overview of Ostrom. I hope the sound is okay from back there. Is this working? One moment. I think it's not taking the right sound. Sounds good.
Since ancient times, man has gazed upwards to the stars. At first full of fear and astonishment, later with awe. Today we watch the sky with increasing knowledge and insight. Although we believe we know quite a lot already, we're always looking for more. More knowledge, more data, more understanding of the universe. Here at Astron, we do fundamental radio astronomy research. Every day we want to explore the universe and our place in it. To do so, we develop state-of-the-art high-tech systems with our hands, our brains, and many advanced tools. Whatever we do with pride and passion. At Astron, the best astronomers in the world work closely together. They cooperate within our international team here in the Netherlands, as well as with our partners throughout the world. Partners like
Okay, so let's just, I almost feel obliged to some PR for what we do at Astron. Just give you a sense of where it is I come from. The middle of the forest in the very remote area of the Netherlands, which, it's, in comparison with Bulgaria, the Netherlands does not really, I think, have remote areas, but in this area it is. So we're quite close to the German border in the northeast of the country, the province called Drenthe. And as an organization or an institute, we basically consist of these two technical departments, or scientific departments. We've got the Astronomy and Observations group, and they're the people that use the telescopes and operate the telescopes ultimately. And then where I'm from, the Innovations and Systems department, that is, we're the people that design the telescopes. So as that clip just showed you, we really design end to end. We start with astronomers with a science question, and we leave, and then we output a product which can answer that science question. That is what we do as an institute. And we have got all the expertise in-house to build these systems with as little as possible external expertise. Of course, once it comes to a system like LOFAR, we can't make 100,000 antennas ourselves. We then give it to external companies to make that. But part of our design challenge is designing a system such that you can make 100,000 of them outside. So that becomes part of the actual design challenge. But the reason why we do all of this is the bigger questions, of course. It starts with the science. So from a science perspective, the questions we try to answer is, how did the universe form, for example? How does gravity curve space? Something we don't really know. With gravitational waves, we now have a sense of it, but can we detect more of that? And for us in radio astronomy, that one of the bigger questions is, what are we missing? Something that's really popped up only recently is something called fast radio bursts. These are explosions in the universe that are just almost, we do not understand how they can be this large. We have no idea what's causing them, and we constantly now detect them. And only almost 9 years ago, the first one was detected, and we still don't know what they are. And this was just because someone happened to look at data slightly differently. Something completely new was seen. And this is why we built these telescopes, is to try and find these things. What are we missing? So just to put it in perspective, I think the physicists among you would understand this a little bit. Maybe just check, if you think about radio astronomy or astronomy in general, we always think of these large optical telescopes, or I do generally, or before I started with radio astronomy, and you get these nice pictures. But to put it in perspective, of course, there's much more going on. You can look at the same object and you see in the visible light or the visible spectrum, you see a particular image, but at radio you'll see something completely different, and at X-ray you'll see something completely different. And the scientists really need all of this information to really understand this object or the universe. Radio, of course, this is where we act at. And yeah, there's a lot that you can see in radio that you simply just cannot see at any of the other frequencies. But we are limited in radio, of course. You've seen such a slide, familiar to you? Okay, so you're nodding. You understand that we can only observe it from roughly 10 megahertz, let's say 3 megahertz on a good day, and typically up to a few tens or middle 50 gigahertz approximately. On, let's say, lower elevation, once you observe at higher frequencies, we need to go up really high. So that's where we've got the ALMA array that's at around 5 kilometers altitude. That's just because we've got these absorption lines from hydrogen and oxygen, or let's say water and oxygen, that is absorbing the energy. And at the lower frequencies, we've got the ionosphere blocking our signals. So we're unable to observe lower than 3 megahertz on Earth. But for that, we can go to space or hopefully the moon one day to build an array there. And at Astron, we've developed these 2 radio telescopes. Are these more or less familiar to you? Have you heard of them, the LOFAR and Westerbork array? Not? Okay, great. We'll be zooming into LOFAR a lot in this lecture. Operative, or the Westerbork array, this one was built in the 1970s. It's actually what we call an interferometer, or LOFAR is also actually an interferometer. Does this mean anything to you, interferometer? Everyone's shaking yes or no? Okay, some people say no. Interferometer in essence is an array of antenna elements. So this they do in order to get an improved resolution. So to image the sky, they use multiple stations. So multiple stations can be either large reflector antennas as a single station, or you can create an array as a single station, separated by a large distance, and then you've got an interferometer. And the main purpose with that is to get better resolution when you image the universe. So Westerbork is just a linear interferometer, and an irregular one that is the LOFAR array. So low frequency array, what do you think is one of the most fundamental questions that we tried to answer with this telescope to the physicists? Why do you observe at these frequencies?
In radio in particular or in general?
In general, why do you observe at 10 to 70 megahertz or 90 megahertz?
We want to see if there's any activity there. We want to see if there's something is emitting in that particular spectrum.
Yeah, what do you expect emits there?
Super distant objects.
Yeah, super distant. Yeah, exactly. What does super distant tell you?
Far
At
in
the
time.
beginning of the universe.
Far
Yeah.
in time.
You've got it right, the beginning of the universe. That was the main question. How did the universe form? That's still the driving question about LOFAR. There's a lot of institutes with other instruments that still try to answer this question. It's quite difficult, even though LOFAR has existed now for more than 15 years. It's still not answering this fundamental question. It's a very tricky observation. But that's exactly it. You've got hydrogen radiating at or emitting photons at 21 centimeters, so 1.42 gigahertz. And this is in our local universe. And as you look back in time, the signal is redshifted all the way down to even below 30 megahertz. The holy grail of, let's say, early universe science sits below 30 megahertz. We can't even observe it from Earth. And this is why we want to go to the moon one day, but that's not this lecture, because we want to observe below 30 megahertz. So if you look at a LOFAR station, there's always 2 types of arrays in LOFAR. You've got the low frequency, the low band array, this one with the patches that's in an irregular configuration. And you've got these black boxes that make or contain the high band antenna arrays. And going in next, I'll zoom into these 2 individually, just to give you an idea of why these things look the way they look. The 2 frequency ranges, 30 to 80 megahertz, you'll sometimes hear me say 10 to 90 megahertz. There's filters that can be used depending, but 10 to 90 is there's extremes in terms of frequency range. Typically we observe only from 30 given the ionosphere. And then you've got the high band antennas operating from 110 megahertz to 240 megahertz. Any idea why not 90 to 110 megahertz, if you were to guess? Maybe you know.
There's something that's maybe consuming that type of.
What happens at 90 or 100 megahertz approximately? I think it's here as well. Basically everywhere where humans are.
Oh, it's some sort of communication.
Yeah, exactly. You say FM radio is right in that band. So the FM radio transmitters are so loud, they create so much radio frequency interference or RFI that we cannot observe there. Low Foscot is located in Europe, and Europe is very densely populated, so there's radio frequency transmitters everywhere.
From 88
And there's no point in even trying to observe there, so we just don't, we cut off that band. This equation I want you to note down, just for yourself. We'll get back to it. In terms of radio astronomy, we have the sensitivity of the radio telescope is our most important figure of merit almost. And how it's calculated is the effective area divided by the system noise temperature. Now I think you may have treated effective area in your lectures up until now, did you?
Yeah.
So yeah, you know that effective area is related to the gain of the antenna. So if you have a certain gain, if you want more area, you just need more gain. Or you can just think of area, fill more area. Then you also get more gain, or in this case, more sensitivity. There's another figure of merit, that's the system noise temperature. I don't think you went into the details of system noise temperature.
We did.
You did?
Yes.
Yeah, in essence, it's your low noise electronics that you want to, especially your first stage. You've got your antenna connected to a low noise amplifier, and that amplifier contributes the most noise to your system. And you want to minimize that. If you've got a good low noise amplifier, you can get a good system noise temperature. But we'll get to that point later. So in total we have over 100, I think almost more than 115,000 antennas in Europe that all together make up the LOFAR telescope. I'd like to now zoom into each of these antennas individually. So first of all, starting with the low band antenna. Have you seen this one before or not? Some of you have. So I'd just like to ask you to look in Mentimeter again. That one. And see if you can indicate on this antenna which do you think is the antenna. Try not to look what the others do. Okay. Okay, so I see the majority of you say the central part here at the top, that is our antenna. I see some of you click on the wires and one of you clicked on the actual, what we call the ground plane, the mesh on the ground. So, no, it's not the part at the top. That contains the low noise amplifiers. So this is where the signals are amplified, and indeed the wires looking like they're keeping the post upright. That is indeed our antenna element. If I tell you this, let me give you a bit more insight. You see that the wire changes a little bit as it goes downwards. So halfway through, you'll notice there's a little loop. So the only conductive part is this top triangle actually. This is just a rubber band keeping the antenna in place. So if you were quick to read in the previous slide that I showed, what type of antenna is this?
Multi?
Sorry?
Multi?
Not quite. I can see why you say this, but close.
E-dipole?
A V-dipole, yeah, exactly. To be more specific, an inverted V-dipole. So you've got a V-dipole that's typically, if you do remember the analog TVs that you had to tune the two antennas, then you can create a V-dipole, but this is just the inverted version of that. So let's look into this antenna a bit. I noticed that you did treat this in your course just at the moment. Why does it look like this?
it to the sky.
Yeah, maybe choose the sky waves.
Yeah, okay, so obviously we want to observe the sky. So let's just start with this, and this is just a recap of what you just did. If I tell you that I've got a half wavelength dipole, so this is lambda over 2, what does the current look like on the dipole? If I looked at the note you did, I think you just handled this today.
It's 0 at the ends of
Yeah.
the dipole and maximum value on the center.
Exactly, yes, so I think you all recall that. It's like this. So now what does it radiate like?
Like a sinusoidal wave.
What do you think the radiation pattern would look like around here? So if this is the dipole, we just said it's 0 here and 0 here, and it's maximum in the middle. Where will the radiation pattern be a maximum?
Like a donut shape.
Yeah, in a donut shape, exactly, with a maximum. That's the main thing with antennas, is if you know what the current looks like on your antenna, you get an indication of what the fields look like. From Maxwell's equations, you'll know that the electric field radiating is directly proportional to, or let's go with the magnetic field is directly proportional to the currents on the antenna. So if you have higher current in a particular area, chances are good that you'll have higher gain or radiated electric fields in a certain area. So the idea of the dipole is we want to get this distribution on it in terms of current. So if you've got that current distribution, then you know you've got your fields controlled to get the most radiated or the most sensitive area in a similar fashion. So yeah, it's called an omnidirectional radiation pattern. A lot of people say donut, but don't use that in technical documentation. So yeah, it has this maximum radiation all around actually. But now, someone indicated in the low band antenna, you looked at that plate underneath, or the mesh underneath. So what's the purpose of that mesh underneath the antenna?
Probably to reflect.
Sorry?
Probably to reflect whatever is coming to the ground radiated from the antenna.
Yeah, in essence you're right, you're reflecting it, but you want to reflect something,
Oh.
in essence you are doing that. So what you're creating is you're creating your antenna to be more sensitive to signals above the ground plane than below the ground plane. That is in essence what you want to create. And there's a certain height constraint that you want to have, and typically this is a quarter of a wavelength above the ground plane. That's where you want to position your dipole antenna. So if you were to think of it, why a quarter of a wavelength? Let's say this field radiates downwards. You'll see that if it travels at 90 degrees. The signal is reflected and it travels back up. And if you follow your vectors, you'll notice that they add exactly in phase again, this reflected signal once it reaches your original signal's radiated again. The moment you deviate from this, these two vectors don't line up perfectly anymore.
So my question is whether it just has to be a multiple of this lambda over 4, or
yeah,
it has to be exactly that.
That's what I mean with once it's multiples, you'll notice that at one point that they'll cancel each other exactly. You'll actually get a null in your radiation pattern. So it's not exactly multiples. But at one stage again, you will get that it adds in a phase, but for off-diagonal angles, you'll get almost a multi-lobe response. So you do not want that. In the end, for radio astronomy, what we want is a smooth pattern. So a smooth radiation pattern, this means that we are equally sensitive to signals all over the sky. The moment that you have what we call a null in your radiation pattern somewhere, you can't detect anything. So that's really understandable for these systems. So we try to keep it at a quarter wavelength or lower even. That's typically what we try to use. And then the last step is, this is just horizontally oriented, but you'll notice that we bent it downwards. And there's a very simple reason for that. You'll notice that this radiation pattern here is slightly axis or anti-symmetric. So it's more broad along the one axis than along the other axis. And by bending the dipoles down slightly, all we do is we broaden the fields. So if you notice along the blue axis there, you'll see that the pattern actually broadens once we bend down the dipole. And this just gives us almost a near axisymmetric radiation pattern at these lower frequencies. And that's in a nutshell the thinking behind this dipole antenna, is to create this type of pattern over a bandwidth from 90 megahertz to 10 megahertz, which is, it's a really simple design, but it operates over a 9-to-1 frequency band, which is enormous in terms of frequencies. If you look at a Wi-Fi patch antenna, that operates in a fractional bandwidth, 10%. I'm talking about 900%. So this is a lot that it works at. So it's decisively simple, actually, but there's a reason for it. Yeah, in essence, then we've got 96 of them, of course, dual polarized, and that make up one low band antenna station. All these signals are amplified at that puck that you saw at the top, that most of you thought was the antenna. Why would that also not be the antenna? What would that thing radiate like? Yeah, exactly. So it's in essence that post is a monopole, so it's sensitive to everything around, and that's also where your RFI sources is. So it's the last place you want to look. You want to have almost no radiation pattern. You want a null towards the horizon. So it's by accident we still also detect, because of exactly that reason, we detect sources from the side. We try our utmost best to suppress it, but it's not always possible. But yeah, so we amplify the signals, the coax cables run through the post in the center, and they're all sent to the station cabinet where they're digitized and then sent off to be processed. Beamforming, you treated this a little bit. If I say beamforming, do all of you, okay, I see someone shaking their head, then I will show you another video. Hopefully this doesn't skip on. To explain what we do with this array, and how do we now get this array to look in a particular direction. That's the concept of beamforming.
Radio telescopes like LOFAR and the Westerbork telescope map the sky by collecting radio waves instead of light, which is what optical telescopes do. When you tune your radio in between stations, you can hear some of these radio waves from space as noise, but this noise contains all the radio waves from all directions in one big mush. To zoom in on a particular patch of the sky, the Westerbork synthesis radio telescope uses 25-meter wide dish antennas. The special parabolic shape focuses waves from one direction only into the receiver. But there is another way. For LOFAR, we use thousands of small receivers without dishes in a technique called beamforming. Suppose a galaxy sends out radio waves. After years of traveling through space, they arrive on Earth and hit our antennas. They arrive at this antenna a fraction of a second earlier than at this antenna. So, to map only these waves, we add a large delay to the signal that arrives at this antenna and a smaller delay to this one. Only then do we add them together. In this way, the signals coming from one direction all add up and amplify each other. For signals from all other angles, this doesn't work so well, so these get filtered out. It is like constructing a narrow cosmic searchlight looking at a small patch in the sky. By changing the delays, we can point our beam at another patch. We can even construct multiple beams at once. This way, we can get a high-resolution image of stars, galaxies, gas clouds, and other interesting phenomena across the universe.
That's a bit clear, right? Just we see the animation like this. Yeah, you have a question?
So the thing that we did was we imagined that we have two dipoles and looked at the field that they would emit, for example, and the conclusion was that by adding more and more elements, we would get a narrower pattern.
Yeah.
But I'm wondering whether this is the same thing.
So where did you add your elements? So you started with 2 here, and did you add them inside or outside, the first 2?
I think I didn't understand the question.
So you started with 2 antennas, so let's say 1 here and 1 there. And then you look at the array factor, I guess, for the 2 antennas. And then you said you added more antennas to get it narrower. So did you add antennas inside these 2 or outside them?
We didn't actually do it. We just looked at 2, and then we were shown a picture of how many a bigger system with many elements would look.
So there's the trick, bigger. So bigger system meaning that the only way you can do what you're saying is if you create this distance between them must be larger. So you need to add, either pull the antennas further apart or add more antennas outside the original 2. As the distance between the antennas, that determines the beam width ultimately. So if you want to make it narrower, then you need to add more antennas to create a larger area. So yes, in essence, that's also what is applied here. That's why the antenna arrays are a certain size, is to create a certain beam width that we want to achieve.
Just one last question.
Yeah.
So this delay in the signal, it happens naturally because those elements are at different distances, or it's something that we do artificially?
Software.
That's beamforming. So these antennas receive the signals from everywhere simultaneously. So every single source out there, even the man-made sources, are detected by the antenna. We save that data, record it, complex data, so real and imaginary. And then we actually have the information from all angles. And then in post-processing, given that we know exactly where the antennas are, we can tune those delays, which is just a phase shift, digitally. And then we can point in a certain direction. So there's a number of ways we can do this, but that's also the strength of these aperture arrays, is that a dish antenna looks in one direction and it sees only that. A aperture array looks at everywhere. So we can, in digital beamforming, look at multiple locations at the same time. And that's why these systems are more versatile than these dish antennas. Of course, there's a limit, because you need a lot of processing power to be able to do that. So you need a very large computer at the back of your telescope to be able to point it in multiple directions. And you need a lot of antennas if you go up in higher frequencies. So we cannot replace dish antennas completely, because at 5 gigahertz, it's impossible to make a radio telescope at 5 gigahertz using arrays. It's just far too expensive. So in terms of beamforming, did you treat these how you beamform a little bit or not?
No.
Okay, so beamforming, there's 3 types. One is all digital, that's what the low band antennas use. We amplify the signals, digitize the signals, that's it. Then you've got hybrid beamforming, and hybrid is we amplify the signals and then we combine them using passive components. So we call them either phase shifters, so this is just phase shifting components that we use to manipulate the phases. Of course, this is frequency limited. Once you set a phase, that's only applicable to a really small bandwidth. Or if we know the delays, we can actually make a delay line, just like that animation showed, that long delay line. We can actually make a PC board with a long delay track and apply that, and only then sum it, and then we digitize. Is it clear why you want to go for hybrid beamforming? What's the advantage of that?
Greater signal.
Sorry?
Greater signal.
Greater signal? There's another reason.
And maybe more resolution.
Yeah, but you can get the resolution with digital as well.
Yeah.
What was the question?
Oh, you mean why hybrid against digital?
Yeah.
Oh.
So what you notice what we do with hybrid is we take a small number of elements, we call a subarray, we phase them up in a particular direction, then we sum it, and then we digitize.
It's less expensive for you.
Exactly.
Because you don't use that much computing power to...
It's the only reason why we do it in radio astronomy. Astronomers want this always, because it gives them ultimate freedom. But here we've got an analog to digital converter to every single antenna element. In a hybrid beamformer, you sum a subarray in the analog domain, so you take your 16 outputs and you make it one, and that you digitize. But now you've already beamformed, so you've made your field of view smaller. We'll get to that now, because that's how the high band antennas operate. We've got hybrid beamforming for the high band antennas. So as I mentioned, all of this digital beamforming happens here in the station cabinet for the low band antenna, actually as well as the high band antenna. We apply beamforming there and then we send the data off. Up until now, I've only talked about one antenna element, and you see this nice, beautiful dipole over ground pattern for this antenna. But what happens to these antennas once I place them in an antenna array? What happens to the pattern? To the radiation pattern of that antenna.
Well, it's not the same.
Yeah, why not?
Maybe because there is some reflection or interaction.
Yeah, exactly that. They couple, mutual coupling, and that always happens, especially depending on the frequency that you operate at. But at these low frequencies, these elements, at 10 meters, 10 megahertz, your wavelength is 13 meters. So within 13 meters, you're already halfway across the station. And there's so many antennas in that area in a wavelength that they all interfere with one another. So just to show you what this actually looks like, this is on linear scale, so not in logarithmic. This is the radiation pattern of one of the elements at around 40 megahertz. This is another one, almost around 40, and this is actually the same element as this one, but at the resonant frequency of the dipole. So exactly where the dipole is half a wavelength long, that is what happens to the central element of the array.
So this
It
is
completely collapses.
This is the frequency at which this coupling is most noticeable.
Yeah, because that's where the dipole is exactly half a wavelength long. Of course, this is only one of the antennas, and every single one of them is different. So this is really a challenge to calibrate and correct all of this. We still struggle with it. It really is a challenge to get it right. But still we can use it. But we can only improve the science by eventually answering and correcting for all these different factors. We're not at that point yet. So this is just something for you to be aware of.
So on the right side, I can see that the scale of the y-axis is much bigger than the other two cases. So does it mean the beam pattern is more elongated in the y-axis or in the...
This is because it's close to the resonant frequency of the dipole.
Exactly.
So it's more signal.
Yeah, there's more fields radiated, or it's more sensitive, slightly more sensitive. You'll see if you look at the band parts of the low band antennas that actually has this peak at 57 megahertz. So this is exactly at that peak. You see it is more sensitive. So well noticed. Luckily, this is for the inner antenna element. So if I go back to here, that's literally one of these right here in the center, where the coupling is the most. Within LOFAR, of course, we have a number of modes. You can select either the inner array, but I'll be honest with you, this one is still not calibratable. Astronomers can't calibrate this one yet because we are having difficulty with the beam model. It is quite difficult. The outer array ignores the inner one. They're the elements of it further apart, and this one we understand really well. And then, of course, we've got an international where you can use almost all the elements as well at the same time in international stations.
And what you said you can't calibrate, what you calibrate for?
We need to know exactly, because remember we need to phase it up to be able to beamform. So we need to know exactly what does your signal chain do to your signal. And that's what's called calibration. So we need to know how much does it change the amplitude as well as the phase of the signal that enters the signal chain. Because once we've got it at the analog to digital converter, that's where we digitize the signal.
Yes.
But your antenna, your amplifiers, your filters, everything changes your signal.
Yes.
So we need to correct for all of that to know what entered our system, because that's what the astronomers want.
Yes.
And that's calibration. Is to correct for all those non-ideal effects that our receiver chain does.
Okay.
And part of that calibration is what was the radiation pattern of the antenna, because that also influences the signal chain.
Yeah.
So, and we still don't know how. Well, we know how, but it's very difficult because of regional coupling. So just to close off this, we'll get back to this a little bit later. If you were to look at these different array configurations, the inner, the outer, and the international, you see, of course, the diameter of the array changes. So you can expect your half-power beam width to change as well. So the inner is quite a broad beam pattern. The outer is a larger diameter, so it's got a more narrow beam pattern. And then the station, depending on the actual diameter of the international station, you've got a certain beam width that you achieve. Asking what you asked about the question. So this beam width was a requirement from the science case, because that's ultimately the largest area that they can look at in astronomy.
One stupid question.
Yeah.
Can you make a station all around the globe?
Can you see the same source
Yes.
all around the globe at the same time?
No.
Because it's radio source.
Yeah.
But only. Yes.
Yeah.
This
So
is
not
the
yet.
answer.
No.
Yeah, this is
Yeah.
the answer.
Yeah. So not yet. We do use it up to the extremes. That's how they imaged the black hole. Everyone, I think, has seen that image, and that's with other telescopes, of course, at a much higher frequency. Because that gets me to the next thing is the resolution of the telescope. So ultimately, this beam width is dependent on the diameter,
Yes.
or the distance between the antennas,
Yes.
as well as the frequency you work at. So, in a nutshell, what we call the resolution is proportional to wavelength divided by diameter.
Yes.
Higher frequencies, smaller wavelength, smaller you can see. And with the black hole imaging, they just use almost the diameter of the Earth, because that station's almost on opposite sides of the Earth, still looking at the same side. But that's what we do with LOFAR, of course. LOFAR is not just one station, it's 52, and it will hopefully be 54 once Bulgaria and Italy join. Then we'll have 54 stations in total, the majority, of course, being in the Netherlands. And what I show here is just a clip showing you how this resolution changes for sources that are observed with this local telescope. So here you can see in the beginning, this is using only the Dutch stations, so the score. But as more and more stations are added, astronomers are able to actually resolve much finer detail of the sources of the early universe. The nice thing with having the next station added is you can see in terms of diameter, it's quite a nice increase in resolution that's added.
So the next one must be in the North Pole.
Yeah, hopefully, well, I don't know, a fiber connection to the North Pole, maybe it must exist already. So yeah, possible. But that's also why this is really a nice station to have into the local telescope. Yeah.
So essentially, it's like making an interferometer with this much of length.
Exactly, yes. Yeah.
But wouldn't you have to have like an insane time calibration and synchronization in order to make sure that...
Yes.
It's limited. So at the moment, each station has got a local Rubidium clock, and we synchronize with GPS signals. So this helps us to get the synchronization up to a reasonable limit. It's not perfect. With LOFAR 2, the next upgrade, we are synchronizing all the Dutch stations. There's a protocol called White Rabbit. This was developed by CERN, and this transmits a reference clock signal through the optical fiber network.
Yeah.
And we're using that, we're deploying that in LOFAR now at the moment to get these much more synchronized. We hope to one day get it through the entire fiber network to Europe, but that's we're not there yet. We're working on that. So to get back to the questions of also why such a fine resolution, just some of the questions again. How does gravity curve space? What astronomers want to do with this instrument is actually look at multiple pulsars at the same time, because you can form multiple beams, And you can localize these pulsars quite well with your narrow beams, given the diameter of these of this interferometer. They want to observe all these pulsars at the same time, and if a gravitational wave passes through space, it will stretch the timing of these pulsars. So you could actually follow this curvature of space or deformation of space by doing that. Not being able to do that yet, but that's why the instrument still exists. We hope to be able to one day. I'd like to go on with the high band antenna. Is that okay? Or do you want to take a quick breather? We continue? So up until now, if you look at the low band antenna, just what type of dipole it is. So now we go to the high band antenna array. As I mentioned, it operates from 110 to 240 megahertz. That's the antenna itself. That is a bow tie antenna. Someone mentioned that earlier, a bow tie. If you were to stand next to these, just to give you an idea, this is 5 by 5 meters, one of these black boxes. So we place, depending on where the station is positioned, we either place 24 of these tiles next to one another, or 48, or an international station will have 96 of these tiles. But just looking at the bow tie antenna, let's go a bit into the details of why we use the bow tie antenna. So we already said a half wavelength dipole has a certain current distribution of a half a wavelength with a maximum in the center. And we position this approximately a quarter wavelength above the ground plane to get that nice dipole over ground radiation pattern. Now, I think you mentioned this a bit earlier, but just to check with you, what happens to this current at twice the frequency, where this is half a wavelength? Yeah, exactly that. You saw that. Now what happens to the radiation pattern?
Not good. We have some kind of parasite signal on the back, so we lose signals.
So where will your maximum be for this radiation pattern? Where maximum? Will it again be here in the center, or?
No.
Yeah. So if you were to look at that, in this case, instead of having it right in the center, you actually have two lobes on the side. Is that a good radio telescope? Yeah, not, because we're in essence completely blind to signals from this area. So the idea with the high band antenna, specifically this bow tie design, is to achieve this 2-to-1 nearly bandwidth to achieve this nice radiation pattern. You might ask, okay, but in the low band antenna case, we use a 9-to-1 frequency range, so 10 to 90 megahertz. Why do we change the dipole shape just to achieve 2-to-1? What's the difference? The difference is we want to control the impedance of this antenna. It's more important. So a bow tie antenna allows you to achieve this radiation pattern with a good impedance match as well. And that's the main difference between the two. Because the impedance match in this antenna is much more important than at the lower frequencies. I can go into the detail, I'm going to just say it. At the lower frequencies, the sky also radiates noise. And the sky noise at the lower frequencies is much higher already than at 110 to 240. So given that the sky noise is that high, we don't care really about the impedance of the antenna. But as we go to the higher band, then we actually start caring, because the noise, the power match of your antenna and your amplifier influences the noise of the system. So we want to control the impedance a bit better at the higher frequencies. But maybe that's too much information for now. Yeah?
Just one question about it. What happens when we have bigger impedance versus, for example?
Yeah, that's
in the noise.
Yeah, so this is going into microwave engineering, but in a nutshell, the impedance that the antenna shows to the low noise amplifier, that influences directly what the noise performance of the amplifier will be. That's in a nutshell. So you can actually tune your antenna impedance to get the best noise performance from your amplifier. And if you want to control your antenna impedance, this is a better design to actually do that. With a dipole, you have much less control. Just a standard linear dipole, you have less control over it.
And why 24 or 48 antennas, not 50, let's say?
Yeah, design choices. I can't give you the exact answer. There's, there are many other factors of cost, for example, just what can we physically achieve with a budget. You could have made more. But
There is no particular physical reason.
No, this was design choices based on resources we had available.
Okay.
If you make your own design one day, you'll have your own your own restrictions on that.
Okay.
But in total, so if you were to take off this sheet, this is what it will look like. You've got 16 4x4 array of these bow tie antenna elements. And as I mentioned, what we use here is a hybrid beamforming architecture. So we apply delays to all of these antennas and sum them as a single output per polarization. So we do this for both polarizations. And then we digitize only these two signals, the two polarizations. So this is the type that we use. In the high band antenna case, we actually use true time delay beamformers. So we have these delay lines that we place on the front end. And I'd like you to quickly calculate that. If you can, you've got calculators with you. If I tell you that the high band antenna separation distance is 1.25 meters apart, this is the geometry that it has, and you'd like to scan all the way to the horizon, what is the maximum delay that you need to have between these elements?
Between every two adjacent elements, or
The maximum delay that you need for that array. I don't know if this is going to work, but if you're ready, you can enter your answer in the end. Let's see what this works. I'll give you 4 minutes. Stop.
And do you guys have a clue how to calculate it?
Kind of. We'll take the horizon as, let's say, 20 kilometers or something?
No, it's just 1.25 meters, so...
It's in between the antennas.
Yeah, so the total distance between the furthest should be 5 meters in
It will be
this direction, and
the maximum distance between any two antennas in the array.
the time that light needed to come from the
Yeah,
first.
so this distance divided by.
Yeah. So yeah, we have 3 answers already. So anyone have an answer ready for that? Yeah?
17.7
exactly, nanoseconds. Everyone got that?
I rounded to 20.
You rounded to 20. Okay. Give or take a few. A lot of engineers do. It's fine. So those that did not get that, you've got 1.25 meter separation distance, but of course your maximum delay will be determined by the largest separation distance between your antenna elements, which will be along the diagonal. So you've got 3.75 meters multiplied by the square root of 2 to get this direction that you have here. And if you know the distance between them, you know that the signal travels at the speed of light, 300,000 meters per second. Then you can calculate the 17.7 nanoseconds delay that's needed. So a delay line needs to be allowed for 17.7 nanoseconds. If I go back to this one. So what would such a circuit look like? If I want to make a true time delay. How do I realize this? Yeah.
I guess I think that I need the wavelength.
Yeah.
And then we could use, for example, reflectors because they should phase.
Yeah. Do you need the wavelength? You think? Because we don't use wavelength now.
No.
You mean the circuit between the actual receiver and the amplifier?
How would I make a 17.7 nanosecond delay on a circuit?
With the long.
Yeah, with long?
Wires.
Let's go with wires. Transmission lines, yeah. So
Yeah,
just a long
transmission
transmission line.
line.
If I know the properties of my dielectric substrate, I can calculate what is the propagation velocity within the substrate. Maybe a bit more details, but in essence, just a line. That's what we want. And that's what we did with the high band antenna. So every single high band antenna, those dipoles, has got one of these inside. And that's the, just the front end, the HBA front end. Now you'll notice here we've got amplifiers, that's for each polarization. And then almost nothing on the board, if you look at it just in terms of size. There's a microcontroller and a lot of switches. And this is some power supply. But the interesting part happens once you take the top layer off and look inside the board. So this is what the board looks like on the inside. And all of these things are meandered transmission lines that we made. So we just packed as many of these lines in between to create all these delay lines. Ultimately, we've got two of them, of course, per polarization. That's the one polarization, that's the other polarization. And this is, if you just look at one of these. So how many delay steps would you actually make? So obviously if you want to look, we now asked if you wanted to look to the horizon. So now we have just one step, 17.7 nanoseconds, and we can look all the way to the horizon. But actually you want to point your beam at various sections in the sky.
Yeah.
So each one of these is a step that you can apply. How many steps do you make actually? How many do you want?
For every degree?
Yeah, for every degree. How many delay steps do you need then?
Yes.
Yeah, how much can you fit in? So this is part of the trade-off when we start. We can't make a perfect, once you go away from all digital and you're going for a hybrid architecture, you're going to limit yourself in this. You need to discretize your beamforming. And you pay a penalty for that because you want to beamform to every sub-degree, the astronomers. But now you can only beamform in certain sections. We use a quantity that we call beamforming efficiency to see what efficiency do we want to achieve. So in a nutshell, what that is we just compare the ideal pattern or array factor we can achieve when we can beamform perfectly with the actual we achieve once we've beamformed in a discretized step. So once we've taken a larger step. Then we look at the beamforming efficiency. So the ratio of those two, that's the efficiency. Does that make sense?
But shouldn't be the efficiency be taken into consideration when you have measured statistically at what distance on the sky a radio source appears?
Yeah, so what I mean here, this is just a quantity we use to describe how well can we beamform in discretized steps. So typically what we have, let's say we want to beamform into this direction. And this is our ideal perfect array factor pattern. So we get this perfect maximum at that point we want. But since we've discretized into steps, we are only able to beamform either in this direction or maybe in that direction. Because we just physically don't have that delay step in between. And then we look at the value, the ratio between this value and let's say that value actually that we achieve. And that's our beamforming efficiency. So we're actually creating a lower gain with our discretized steps than what we have once if we could have beamformed perfectly. Follow? Yeah?
My question here is only whether, so this doesn't stop us from looking at any point in the sky, it just makes, for example, the noise that we would see bigger.
Oh no, I
Not
think
the noise.
resolution is the trade-off, isn't it?
We lose sensitivity because we lose gain. And the gain causes a loss in effective area. So here you see the array factor is at maximum, we're in the ideal case, but because we have a discretized step, we're just pointing off it. Because we cannot apply that perfect delay we want to. So our beam gain is actually slightly less.
The noise cancellation works as usual.
Yeah. So, but that's a price we pay. And all of that introduction is just to show you what the effect is, so how you can change this beamforming efficiency. So how can you get this, how can you choose the optimal discretization step to get the best efficiency over your hemisphere. This is what we try to show here. So each segment here is just a segment of the sky, and this is a 0-bit beamforming, so just looking up or looking in one direction. A 1-bit, meaning we can either switch between two steps. A 2-bit, so we can use 4 steps. 3-bit, 4-bit, 5-bit, how many steps you can have in between. And as you see, as you increase your number of bits, so the number of steps you can take, you increase your efficiency. So here the red is 100% efficient and the blue is almost 0. You cannot get your array factor, match your array factor to the idle case at all. So for the high band antennas we use a 5-bit beamformer, and there we get 90% beamforming efficiency, so we get to 90% of the idle value over almost the entire field of view. So this is what they look like. These are the delay steps that we can select. And each of them is roughly half a nanosecond that is added. And we are able to select these half a nanosecond increments and steps, sizes of delay, to be able to beamform to any area of the sky. The total that we can apply is 15 nanoseconds. And I just asked you what is the maximum that you need to scan to the horizon. So what's the price that we pay?
Cutting off the part of the sky.
Yeah. So if you look at the beamforming efficiency for 70 nanoseconds, you'll see that you can achieve this greenish yellow is 90% over the full sky. So this is right up, and that's the horizon. But with the 5-bit 50 nanoseconds, you see along the diagonals, the efficiency just drops. So with the high-band antennas, they're not very sensitive along diagonals, just because of the way that we apply this beamforming.
Why couldn't we make it 17 nanoseconds though?
Yeah, good question. This was another design trade-off that was done. So yeah, good question. As I told you, these were done by my previous colleagues. It's a design trade-off to make them saying that, okay, typically we don't observe all the way to horizon always. Yes. Although there are now use cases where we want to observe the sun as long as possible, for example. But at that time, we're under time pressure as well, and you just have to make a decision now. We have to build within 3 months. So then these design choices but we do make the trade-offs. That's why we have this graph, because this was during the design phase. The engineers had to show, look, this is what you pay.
But this is the perfect point of view when the surface is flat, when you have terrain and mountain.
Yeah, then of course then you can't see the either way. Yeah, they're absolutely. In the Netherlands, we typically don't have this.
Yeah, I know. Here there's mountains.
The mountains also shield you, so the mountains are a good thing actually sometimes. Yeah, so in terms of field of view, this is actually then, if you look at a single antenna element, you've got this really nice broad field of view. You get signals from everywhere almost. But then we combine them into a tile, and this is then the output that we digitize. So you see in terms of field of view, there's actually quite a large portion of the sky that you just fall away, or that you ignore once you've beamformed. And that's the price you pay for going for a hybrid beamforming architecture. Because now it's digitized, so your interferometer, so if I take another station, can now only look at an object in that beam. It cannot look outside of it because those signals are already phased out. You don't see them. So as I said, the last step is then combining these tiles together, and you see the much narrower beam that you get from the tile. This is again a digital beam, so we are able to fill up this entire area with multiple digital beams depending on how much computational resources we have. So we can digitally beamform an entire circle of beams within this area if we want to actually create a larger image of the sky. Don't know if we're going to get to this part, but maybe we do. Half power beam width, I don't know if there's an approximate formula for that. It's quite useful to use. And this is of course in radians. Everyone knows how to get from radians to degrees? Yes, I hope so. So yeah. But in essence, you see again the wavelength and diameter dependence on the beam there. This is only for regular arrays and linear arrays. You get this approximate relationship to get to the half power beam width. I told you that there are 3 types of high band antenna configurations. So we've got in the low-far core within the Netherlands, we've got these 2 stations of 24 tiles. For the remote stations within the Netherlands, we've got 48 tiles. And for the international stations, like the station that come to Bulgaria, it'll be 96 tiles. So of course, it goes without saying in terms of beam width. You get the international with the smallest and the narrowest beam width. The nice thing to notice is though that the side lobe levels of these regular arrays are all typically first side lobe level minus 13 dB. And that's just standard for a regular array. I'm going to run back because just look at this array factor pattern. We've got main beam, minus 13 dB side lobe level at the most, and then it just reduces downwards. If you look again at the array factor of the low band antenna, you notice the side lobe response then. So why did we even decide to do this? Why would we go for an array configuration that looks the way they do, like this, completely irregular?
Maybe to not reflect signals towards the other antennas.
They reflect towards one another if you look at what happens to the beam pattern.
Yeah.
They really influence one another.
Doesn't it mean that you can observe a bigger region of the sky this way?
No, not necessarily. The antennas see the entire sky. Why did we decide to go for a random in this instance, and then for the other again we chose regular? Because this random, you look at the side lobe level, it's minus 11. Here we've got the, I don't know, say 27th side lobe, for example, at minus 15 dB, whereas the high band antenna was much lower already. And remember, there's a strong source here, or this area of the sky, that signal enters your signal chain. So why did the designers even decide this? Did you handle grating lobes? grating lobes?
We measured that, but
If they went, that's what I'm testing. So a grating lobe. What happens if, let's do this. This antenna is a wavelength apart. These two are separated with a wavelength. If my signal is incident from the top, how do the signals add? In phase or not? Do they add?
They should be in phase.
Yeah, they reach the antennas at exactly the same time. So yeah, they should be in phase. That's not just assuming that all I'm doing is I'm adding the signals from these two. If this is a wavelength apart and the signal is incident from this side, it enters this signal at one point. So let's say it's a maximum. Then it goes through a wavelength. Oh, was that right? No, that was not right. My bad. So like this. Ignore that one. So once it enters on this side, the signal travels through one wavelength and then it reaches this side.
Phase.
Exactly in phase again. And it adds again. If the signal's coming from the other side. So how does this array know that where the signal's coming from? There's 3 angles and all 3 of them add in phase.
So it has to be, it should not be symmetric if you want to know the direction from which the signal is coming.
They should not be a wavelength apart if you want to know this. And if you were to look at this array factor, you'll notice that the array factor is actually, let's assume this antenna was in free space. It'll have 4 lobes, because all the signals add in phase from all those directions. And that's purely because of the distance that they're separated with one another. So when you design an array, you need to take this into account. There's another step. This was we're just adding it. Once we start adding delays, then the separation distance changes. So the rule of thumb we use in radio astronomy, because we scan to the horizon, is we say that the antennas must be half a wavelength separated. Then you can scan all the way to horizon, and one of these, what we call grating lobes, will not appear. One of these additional maxima will not be in your field of view. But this limits you, because if your antennas have to be half a wavelength separated with one another, and I design it at the one frequency, at twice the frequency, then that's already happened. Then they're already too close to one another. Half the frequency, sorry, I'm going the other way around. So this limits my frequency bandwidth to 2 to 1 actually. Then I will get a grating lobe either way. And the low band antenna operates over a 9 to 1 frequency range. The only reason why we could get away with it is by scrambling all the antennas to make sure that these maxima don't always add at exactly the same frequency. And that results in this type of pattern. So we introduce this irregularity to make sure that they don't add up any constructively from any particular direction, but in the direction where you want to look. More or less.
And when they add up constructively, this happens for a specific wavelength.
Yes.
Yeah.
Yeah. And this allows us to use the array with one maximum beam pattern, but it comes at the price of higher side lobes. If we now go back to the high band antenna, you will notice at the highest frequency, at 240 megahertz, these grating lobes appear. So we have a broadside beam, but at the horizon we've got these 4 patterns. Our element spacing of 1.25 meters within LOFAR is actually still too far apart at the highest frequency. And that's where you still get these extra maxima, where the signals add in phase. How did we get away with it?
what you mean, why isn't this a problem for observation?
Yeah.
Because we don't care what we observe from the horizon?
So let's say I'm observing a very faint star here, and the next moment the sun comes up. Then all that energy from the sun enters my system, because I'm equally sensitive in that direction.
Maybe we use polarization in some way?
There was a neat trick that we had, and this was something that was unique in the sense of radio astronomy or interferometers, that we're adding stations that are separated a lot by one another. They're actually now considering a similar thing for 6G systems based on this type of concept. But radio astronomy was one of the first where we could actually use this. And that was, we rotate the stations. So if you look at, this is our beam where we're focusing. No, that is our beam where we're focusing. The green ones are the grating lobes. So if you look at high band antenna stations for the entire LOFAR telescope, all of them are rotated with respect to one another. Because they're rotated with one another, you apply a slightly different delay to look in a certain direction. So your grating lobes are also at a different location in the sky. So for the one array, you have a grating lobe in the one area, and for the other array, you maybe have multiple ones. But you notice that these are actually, if you were to add them, they don't add together. It's only the main beam that adds together. The rest add in a null of the other station. So per station, yes, you get a larger signal from something in your grating lobe, but once we use it as an interferometer, we'll get away with it.
Yeah.
So that was just a neat trick that helped us to get away with that. Of course, for the low band antenna, there's just too many areas where we get grating lobes given the bandwidth. We had to go for an irregular array. We're still debating within Astron which one is best. There's always a team on each side. So just to conclude this, this is in essence how the beamforming works in LOFAR. You've got a dipole, either in the case of the low band antenna, or a tile in the high band antenna, and this gives you a rather broad field of view. Then we add a station or a subarray. This gives us a narrower field of view. You can choose to, even within one tile, beamform in different directions. Slightly reduced sensitivity, so take some tiles and point them in one direction, another tile, point them in another direction. So you can get multiple pointings. And once all of that is digitized, then we can create these very narrow beams and multiple of them. In total, you can create with LOFAR 488 sub-beams that we call. So you can create 488 beams within one of these station pointings. That's just what we've limited in the back end.
Just one question. So at some point in the presentation you showed a picture of, I think, a galaxy that was taken from different instruments, some in visible light, some in radio. So I wonder how, for example, you can take a picture of a galaxy. Is it something that only one of those beams would detect, or how do you actually get?
All of them detected actually, but they all detected from a slightly different angle. And it's a combination of all of these slightly different, detecting something from a slightly different angle that we can use to create an image from.
Okay.
There's a mathematical transformation. It's actually a Fourier transform that we use. But it's a Fourier transform that's based on the relative distances between antenna elements. That is what creates your resolution in the end. So what we want to, when you create an interferometer, we want to create a large amount of relative distances between antenna elements. That's a different course.
So,
yeah.
imagine.
A related question would be, for example, in optical interferometry, do they have to, again, have a very narrow, I think, like not a whole telescope taking a whole picture, but just one point, and then another telescope taking a picture of just one point of the sky and doing the same thing?
They do optical interferometry already?
I don't know actually.
I don't think so.
They
Because
don't do
I think
optical
the synchronization would be you're at such high frequencies, synchronization, I think I've read that they want to look into this, but I don't know if they do that already. Because of the accuracy in synchronization you'd have to achieve, I think. So with optical, then you've got actually a CCD image that you can create. So they've got multiple sensors that actually just detect the photons from a certain area. In radio astronomy, there's you can just say we use imaging, the transformation of imaging, but to explain that to you in 5 minutes. I hope there's going to be a local data school or something that you can attend to just, because then they really dig into this. It's imaging theory. It's a simple Fourier transform, but the trick is it's a Fourier transform that is defined from the visibility plane, and the visibility plane is created by the distances between your stations. I can't tell you more than that. It's a long discussion. I am looking at the time. I ran over my own time actually.
Almost.
Sorry, but time is gone.
Yeah, you have to go. Yeah. I had a lot more that I wanted to discuss, and there's actually an array architecture design study I wanted to do with you. But I'm going to keep you possibly for another 40 minutes. And on one stage also find enough is enough. So it's up to you. You can go through an array configuration study, but I know you've had an extremely long day yourselves. I took slightly longer through this presentation than I wanted.
Let's do it.
You want to go through it?
Yeah.
I'm happy to stay as well. Thank you. So then we can just use these two equations that we wrote. This is to put it all together for you. You're welcome to just take a quick breather if you want to. I think maybe that's good. But then I don't mind that, but nowhere else to be. So if you're okay to stick around for a little bit more.
How many minutes would you need for the explanation? Because personnel is also involved here.
Okay, what time should we leave?
5:30 something.
Can we skip the break then?
Yeah.
We go on. Yes, then 5:30 we cut it short. I'll help you with the assignment. Let's just open the right one. Okay, so it's okay, I'm just going to continue. Have you heard of the square kilometer array telescope? Okay, I have a video for it, but it's going to steal our time, so I'm just giving you a quick introduction. This is going to be the largest radio telescope in the world, so at the moment LOFAR is, but this will beat us. They're going to be much larger. They're building it in 2 continents. They're building it in Australia and in South Africa. And it's a very large frequency range, starting at 50 megahertz, going all the way up to, I do not know exact, 15 gigahertz at the moment, but they want to go higher eventually. They're building these aperture array stations, like LOFAR stations, in Australia, and they're building dishes in South Africa to cover these 2 frequency ranges. There's a wish, they're not building this yet, but one day in the future, they want to build a very dense aperture array. So an array telescope with, a planar array telescope operating from 450 megahertz to 1.45 gigahertz. So the idea with that is to create an instrument that observes at these frequencies but can have multiple beams because a dish can only point in one direction unless it has a phased array feed. But mostly they just look at one direction. So there's a science case that really wants to have this middle instrument that they call the mid-frequency aperture array to observe from 450 to 1450 megahertz. So there's been some demonstrators. Austin built this one. That's 20,000 antenna elements, and this is connected with all the array. And the idea is to just create this large area of antennas that can look at multiple areas in the sky at the same time. But there's been more demonstrators. I want you to take this requirements. This is typically how it works. You get from the scientist, you get this list of requirements, and they tell you make a telescope. This is how it starts. So we get a frequency range. They tell us an optical field of view, a scan range, how many independent beams they want, what the sensitivity should be of the telescope, and what's the system noise temperature that they want. This is typically where you start. Where will you start with this? How would you start making such a telescope?
First, I guess the frequency range, right?
Yeah, okay, and?
So we would have to have some kind of it's an array, right? So we have to choose a design.
Yeah.
And
with what will you start?
For a single element.
Single element?
Yeah.
And what do you need to be able to make a single element? What do you use?
Well, just the frequency should be enough, right? Because that would be defines the dimension of the.
It's one that you're missing, and that's the half power beam width. So if you look here, you've got a scan range requirement as well.
Okay.
So you want to make sure that you've got an antenna that's also sensitive up to 60 degrees scan range.
Okay, yeah.
And typically we can use that as a half power beam width requirement to say, okay, operating from that frequency range, but also having a half power beam width of 120 degrees so that we can scan our array up to 60 degrees from zenith. So we can make it an antenna at least. Well, we know what our antenna should perform or where, in what range of antenna should be performing. I can tell you though that 120 degrees half power beam width is very difficult to achieve over that frequency range, but that's something else. How do we now get to the number of antennas? So we know more or less what our antenna should do. We can now go and look for an antenna or design an antenna that gets really close to this, but how many of them do you need? And which requirement do you use to say how many antennas?
Maybe this restricts our field of view.
Which one do you use? Field of view. So which one do you say do you use?
I said that the number of antennas restricts the field of view.
It does, yes, to a certain degree, yeah. But which other requirements can you now use to say which one, how many antennas do you need?
The sensitivity, I think.
Yeah, what will you use to?
Well, the formula we have, so basically the more distance we have between the
effective area.
Yeah, that's what you want to get towards. So we know the sensitivity, we know the system noise temperature, we can get to the effective area. How far should these antennas be separated from one another?
It should be more than wavelength.
Which wavelength?
So it would be the bottom value, the 450 megahertz.
In this far, and that twice the frequency?
Twice and 3 times. So the range is 3 times bigger.
So you want it to be a half a wavelength spacing actually. Remember that you want to have no grating lobes when you're scanning anywhere. So if you scan, if you want to ensure no grating lobes when scanning, half a wavelength separation distance is required. When you're only looking up, then a full wavelength is required. But once you look towards the horizon as well, then you need half a wavelength separation distance. And you choose half a wavelength separation distance at the highest or the lowest frequency.
Well, that was going to be my question, since it's a big range.
Yeah.
How would we choose which one? So
So
it would not be a problem if we have smaller wavelengths. will problem if we have bigger ones.
So I have a distance, these two antennas are this far apart. At f0, they're half a wavelength. What are they, how far are they apart at 2f0?
Twice.
They're a full wavelength. So then they're too far apart.
Okay.
So I choose at the highest frequency, because that means electrically, my antennas just become much closer to one another than half a wavelength at the lower frequencies, which is good, that I want. I want it to be less than half a wavelength.
Yeah.
So that's how we can calculate the number of elements. So from that we've got the effective area and we've got the maximum element spacing, where we said we use the sensitivity to calculate the effective area. And if you were to calculate this for a sensitivity of 10,000 square meters per Kelvin, given 40 Kelvin system noise temperature, you get to 400,000 square meters. That's what they want, the astronomers. If we say we want no grating lobes, the distance must be below the smallest wavelength over 2. And if you were to calculate that, you get a maximum element spacing of 10 centimeters. Then the question is, which array configuration do you use now?
As far as I remember, the irregular one was chosen because we were looking at the lower frequency spectrum.
Mm-hmm.
So coming from that, I guess we'll choose the regular one.
Yeah, we've now designed our system to know that there's going to be no grating lobes. Our antennas are spaced 10 centimeters apart, knowing that even if we scan all the way to the horizon over our entire frequency range, there won't be a grating lobe. So we're okay. If you were to look at the array factor response, you see a regular array is much more well behaved. It's got one beam, and then it's got minus 13 dB side lobes, and it only goes lower. It's a much better system to calibrate. So let's go with regular in this case. How many antennas will you have in 1 square meter then? If the elements are 10 centimeters apart.
100?
Yeah. How many do you need for 400,000 square meters?
200 times to the power 5. Oh no, that's the effective area, right? It's not.
So you need, yeah, that's the collecting area that you want to achieve.
40 million?
Yeah. That's the amount of antennas that's needed for this telescope. That's also the reason why it does not exist yet. But this is getting close to what they want. That is why they're building the other two extremes, but we're still working on making this possible one day. If you see that you do need 40 million antenna elements for this instrument, how will you beamform such a system?
I have, maybe it's a bit weird question, but isn't that everyone has a mobile phone which has an antenna? So is it possible to utilize the mobile phones of millions of people as like interferometry?
Well, synchronization will be a difficult one, I think, with that.
Maybe through an application that do that automatically.
What we are looking at.
The phones do not have a very accurate clock.
Okay.
So synchronization is a problem. What's the polarization of my antenna now?
Yeah, it changes all the time.
And what is it now? What is it now? That's these two antennas are designed for that polarization diversity. But for science, we need to know to be able to get it. Yes, you've got gyros and things in there. You can discern it afterwards if you record it. So not a bad idea, but we have projects where we're looking at building low-far antennas at home, so making it possible for the community to just go install these things at home to do that. So it's not a crazy question. We're thinking along that, but we're not there yet. back to this, how do we beamform 40 million antennas? What's realistic?
Maybe there is a way to first look at how far they interact with each other. So, and then look at just part of this picture and try to then say that this is one effective antenna, and then look at how they interact together.
Okay, but
basically in groups.
in groups, yeah. Okay, so I think the word you're looking for is hybrid beamforming. The reason for that is just if you were to take 40 million analog to digital converters, it's enormous in terms of cost. So we cannot create a system that is digitizing all of these antennas individually. We need to use a hybrid beamforming scheme. So either using phase shifters or using true time delay like we did with the high band antenna. The question now is just, so you're creating subarrays or you're creating tiles. How large should this tile be? And can you derive that from this requirement? I don't expect you to because there's a new term in here, but maybe you can figure it out just looking at it. What does optical field of view tell you? You see, it's measured in square degrees. This is a bit of an abstract concept, but to try and illustrate it, if you were to look at the moon, and you to look at the optical field of view that the moon has on the sky, and measure that surface area in terms of degrees squared. So typically we have this in terms of meters squared for just a circular surface, but that circular surface on the sky you see measured in degrees squared as you were to measure a beam width in degrees. That's called the optical field of view. So I told you that we can define the half-power beam width in terms of a ray diameter at a certain wavelength. This is just a standard approximation. And we know what the area of the surface is, or circular surface is, in terms of degrees. We can use a combination of these two formulas to solve what must the diameter of my array be to get that field of view in square degrees. You follow that thinking? Yeah, you just have to trust me. I know you just seen this for the first time, but that is literally how we need to use this requirement. So when we've designed our prototypes, we use this requirement to derive what must our subarray size be, because that is, remember, like with the HPA tiles, you've got a raw beam pattern, and then you've got a tile beam pattern. And only within that tile beam pattern can you place digital beams. So that determines the field of view of your telescope. The tile beam pattern. And that determines ultimately this requirement, decides how large can a tile be. So as I say, if you plug these equations into one another, you get a nice expression like this. For which to solve that you need a half power beam width of 16 degrees for your antenna or for your subarray, and that results in a diameter of approximately 1 meter for your tile size. I'll be sharing the slides with you, so just go through it, just together with that equation, write it down for yourself and you'll see that. So from this set of requirements, we can see that, okay, what type of antenna element we need, what is the minimum element spacing that we need, and also what must the tile size be in order to have an optical field of view of 200 square degrees at 1 gigahertz. This is more or less than what such a configuration will look like, just in terms of a array factor, for example. Not assuming we don't know what the antenna looks like at the moment. But there's one requirement here that we've not looked at yet. We need 2 independent beams per polarization. And how would you achieve that? So you've got the low noise amplifiers connected to antennas, you have phase shifters, for example, or true time delays, you add it and you sample it. How do I create a second? That's one beam. How do I create a second beam?
Maybe we use dipole antennas like to measure the polarization in two directions.
They wanted per polarization. So each polarization, they want to point in two different directions.
So it's like 8, each antenna like 8 wires.
You're not necessarily pointing in a different direction there because remember, once we beamformed, we pointed in a direction. So how can I beamform in another direction? How can I create a front end that allows that? What do I need to change on this architecture to do that?
You just need to have a phase shifter, right?
Another phase shifter, right?
Yeah.
Where do I add that? Where do I connect that other phase shifter to?
Parallel maybe?
In parallel, yeah, but what I need to then before, how do I get that parallel signal?
Before combining the signals.
Yeah, before.
So after amplification, I split my signal in two.
Yeah.
Simple, power divider. So I amplify, I add a power divider here. The one signal goes to the one set of phase shifters, the other signal goes to the other set of phase shifters. I sum both individually and I digitize both individually. That's how we've been doing it in our demonstrators as well. So this 20,000 element demonstrator has got exactly that. It's got an amplifier of each antenna element, then a power divider, and then we've got two sets of beamformers that can individually steer two beams into two directions of the sky, and we digitize those two. And we group these into subtiles of roughly 1 square meters as well, to be able to achieve that 200 square degrees field of view that's required. We stopped at this because it's becoming too expensive and they first want to build the other part of the telescope, which I understand. But maybe by 2035 we will build these again. We'll see. As I said, I'll share this slide with you. This was going through it really fast, but I hope it gives you an idea of what it takes or how you start building these systems from a small set of numbers. Then I'm done. 5 minutes. Thanks, Peter.
Perfect.
Yeah.
Perfect.
You have 2 more days.
Yes.
Yeah, but this was all on antennas then now.
Yeah. Folks, do you have questions?
Will we have a lecture with you tomorrow, or was it all?
No, today was full, but I share my contact details with you, so if you have any questions, just feel free to email me. I always can write it down for you. I'm happy to even schedule a meeting with you if you have questions. It counts to all of you, so not a problem.
So, if you have any questions for particular strong design, David is the man.
Or I can put you in contact with another person that could help. But yeah, Prinsloo, that's our logo at Oslo. So please, if you have any other questions.
I have, but they're not related to design, they're more general about Astro. So, will it be used to observe the sun? And yeah, that's the first.
LOFAR, to observe the sun?
Yeah.
Yeah, it is absolutely used to observe the sun. I can show you, while preparing for this meeting, I stumbled upon this from a colleague of mine. And here he observes the sun. So what he does, he takes the low band antenna array, because that's all digital, that's really nice, that's the sun, and he makes all of these beams across the sun, and he follows the sun. And he did this, and while he did that, he was lucky enough to see a solar burst, so the sun erupted. And here you see the image that he created, and within this beam, he looked at this frequency spectrum. So this is frequency from 40 megahertz up to 90 megahertz, and this is time from 0 to 120 seconds, I think. So you can see in this beam over frequency, this is how the sun erupted. So you can look both spatially, where did the sun erupt, and also what did it do over frequency. And then you can see how the sun, or the flare in time, actually propagates further away from the sun. So yeah, they observe the sun at the moment.
Very nice.
But again, this you can't do with a dish. The dish will be looking here potentially, and he misses that. So it's also only because we have the resolution with low fi.
Single station?
This was a single station. Yeah. You had to write quite a campaign to get access to a. Wait, no, this is not. He used the core, I think, for this. He used the core for this, not a single station.
The resolution is very high, actually.
It's tide array beams, so he used the core stations for that, because these are synchronized stations. So yeah, no, not a single station. If there are no more, then yeah, please, you've had a long day.
Amazing things, guys, aren't they?
Yes, indeed.
So,
Thank you.
Yeah,
thanks,
happy to be here.
David, for the. Very nice. And I thank you for holding tight so far because it is exhausting day. It's not that easy.